Oh, it seems we're online, Maurice.
Are we on?
I guess we should be trying to say something clever.
We truly are on. Okay.
All right.
Good evening. Hello. And thank you for coming to our talk on the sincerest form of flattery. So I really like to create abstracts with intriguing titles. I never have ordinary titles, but José reminds me that not everybody will know what the sincerest form of flattery is if you're not a native English speaker. So there's a saying...
Which is my case, by the way. Which is my case, by the way.
Right. So there's a saying in English that the sincerest form of flattery is imitation. And the idea that I had for this talk was that I've known functional programmers. They're very irritating people, and I've been around them for several decades, and all this time they've been really smug about how much better their ideas are, and I've been kind of quite satisfied that in all that time object-oriented programming has been so much more popular. But actually what we notice is that although functional languages have not made it that much to the mainstream, the ideas of functional programming have come into object-oriented languages, and the idea of this talk is to study two ways in which they've come into two different languages. So, I'm Maurice Naftalin. I have a slide here which just talks about the ways in which I combat my insecurity about being in front of you. These various things that I've written a couple of books on Java, and I'm a JavaOne Rockstar, as JavaOne used to be, and so on. So that's me, and this is José.
And my name is José. I just gathered some links that you can follow on this slide if you're interested in the content I'm producing online, and including my Twitter account. And if you don't like to be spammed on your Twitter timeline, you can follow me, and you'll be perfectly contented with that. And before we start, we would like to talk about a marvelous event that it turns out you're organizing something in this wonderful city of Edinburgh, and I can really only second you in advertising this event.
So people may have heard of unconferences. So J-Crete is now the most famous unconference, and right, and I've got some applause for J-Crete
in Scotland.
But J-Alba is actually really a very good unconference as well. So it's running for the third year in 2020. The dates are already fixed. The website and the Twitter handle are on the screen there. It's I believe it's a pretty good event.
I believe so too, yes. Yeah, I've been there twice.
Right.
So I didn't miss any, in fact.
So that's not what we came to talk about. But I would encourage you to pre-register. Pre-registration will increase your chances of getting into the unconference, and particularly on getting onto the trip afterwards if you're interested. So what we're here to talk about today is functional programming, and the ideas of functional programming in particular. So functional programming has always been attractive to people who are really interested in a form of programming which could be mathematically analysed, and the title says it really. It's elegant, it's mathematically sound, and several ideas have contributed. The ones that we're really interested in here that form a kind of core of functional programming are higher order functions, which is absolutely the essence of it, but also parametric polymorphism, which has appeared in object-oriented languages as generics, that's what we generally call it, and pattern matching. And these ideas, as you can see from the dates on the slides, have been around for really quite a long time, and they've formed part of the kind of the culture of functional programming. Functional programming hasn't caught on in the mainstream because it's often not practicable. The emphasis on immutability has meant there's been far too much. I mean, particularly in the days when memory was much more expensive, but even now, pure functional programming can be very inefficient, and so it hasn't really caught on in the mainstream. But the ideas of it are really very, very important. Object-oriented languages, by contrast, have been very successful, but they often aren't all that elegant. So some features are good. So subtype polymorphism, which we know as inheritance, has been very successful, I would say. Strong static typing has been a feature of all the object-oriented languages that we like, and of course automatic memory management has to go along with the constant dynamic creation and garbage and collection of objects. But object-oriented languages, despite their success in the mainstream, have always really suffered from feature envy.
I would like to move here, if you don't mind. Just for this slide.
just for this slide.
Yeah.
You can match up your speakers with the content of the slide. So the starting point for our talk here was the pizza paper. So pizza was an initiative that was.
Oh, it's okay.
Now you can move back. Now you move back again. Pizza was a paper that was written by Martin Odersky and Phil Wadler back in the very early days of Java. Odersky describes this in an interview that you can still find online as the situation was that one of Phil's students came to talk to him about this whizzy new language called Java, which was going to catch on. And people like Phil, who I know very well, one of my books was written with him, is always on the lookout for something fashionable. He's a very strong academic, but he's also always on the lookout for important commercial ideas that will make his work relevant. And so they couldn't resist, when Java was clearly going to be very important, they couldn't resist seeing, could they add those features, generics, higher order functions and pattern matching to Java? And the result of that attempt was the pizza language, which essentially was a superset of Java. It was a strict superset, so you could write Java in pizza, but there was a translation scheme which would take the language which contained these three features as well as all the rest of Java and would translate it into Java. And in the pizza paper, they actually lay out that translation scheme, and they actually had a working implementation for it. So what happened was that from Pizza they approached Sun with microsystems with this, and the result of that was another language called generic Java, which was done in collaboration with two people who were working for Sun at the time. And generic Java attempted to take the ideas of Pizza and combine them with Java, addressing a really important problem. The problem for generics is that it's ideally you will carry the parameterized types into the runtime. But it turns out it was impossible to do this because not only because the VM doesn't carry runtime type information, but also because it was necessary to be binary compatible with legacy ungenerified classes. And this was really important because the key, a really important design goal of all Java changes has been to maintain backward compatibility. So at that point, after generic Java, the path divides because Martin Odersky, having worked with this, was just frustrated with the restrictions of the backward compatibility imposed onto Java and the various wrinkles and corner cases that it put into generics that we're going to describe in this talk. And he went off and created Scala to start again almost completely from scratch. Not quite, but almost completely. And meanwhile, the generic Java went eventually into Java 5 after 6 years of waiting. So Java's been kind of pretty slow to take these ideas up because of the constraint of backward compatibility. We got generics in 2004, in Java 5 eventually, after missing an entire release of Java just because of various political problems. Higher order functions eventually came in the form of Lambdas in 2014, and pattern matching is
coming
sometime soon. Sometime really soon, I think. Yeah.
So niche.
Yeah, soonish. Scala didn't have these problems because you will see the really, really careful and intricate design decisions that had to be made for Java to ensure that the backward compatibility would be maintained. Scala didn't have most of these problems. It still had to be interoperable with the Java runtime with the JDK libraries, but that was all really effectively. And then they had to make some kind of concession to accommodate wildcards in Java, which are a rather weird thing that we're going to go on to talk about. So they aren't entirely independent of Java, but by and large, they could go their own way. And so Scala could eat its pizza all in one bite. And in fact, when in 2004, the first version actually incorporated all of those features. So what were the real problems that they had with these incorporating these features into Java, taking account of the backward compatibility. We're going to divide this talk into 3 parts. So first of all, we're going to look at generics, then we're going to look at higher order functions, and finally we're going to look at pattern matching. And for each of those 3 parts, we're going to see what happened in pizza and generic Java, then what happened in either Scala or Java, and then what happened in either Scala or Java. So the order varies. So what were the problems with generics then? That's the first one. The problems with generics were really big problems, were twofold. One of them was the problem about type information availability at runtime, which I've already mentioned. We couldn't make it compulsory for a generic scheme to be able to rely on type information being there at runtime type information. We couldn't rely on it, not only because the VM didn't support it, but because legacy ungenerified classes didn't have it, and it was really important that right from the get-go that the newly generified Java code should be able to interface with libraries that hadn't been generified. And so essentially the only thing, the slide here shows that at the bottom line of the first bullet of the first frame says we actually can't make an integer array just from a list of integer. The reason being the list of integer doesn't contain runtime type information, and arrays were the one thing, or are the one thing that does have type information. So an array knows what type it's been created with, but it's the only kind of collection that does, because arrays date from Java 1.0. And so, in fact, to make a new array, you have to supply an old array, essentially. In our book on generics, Phil describes this as being analogous to the old saying that in order to make money, you've got to have money. So in order to create a type at runtime, you've got to already have a type at runtime. So that was a big problem that they had to overcome, and we'll go on to talk in a moment about how generic Java overcame that problem. The second problem was the particular scheme that they chose for array subtyping. Now, arrays, the problem was that we wanted what appears on the bottom line there. We want to be able to have a generic method for sorting arrays, and you really have to have that in a language library right from the get-go, or if you can't do that, what can you do? So in order to do that, their idea was that they would make arrays covariant. Now, what that means is that in the case of if you look at the top slide, you can see that you can assign an array of integer, a reference to an array of integer, you can assign that to an array of number. Integer is a subtype of number, and a covariant typing scheme says that an array of integer, therefore, is a subtype of an array of number. And this was their solution in order to be able to write what appears at the bottom of this slide, so that they could have a generic method for sorting arrays that would work with any type. But it turns out that this was actually a ticking bomb in the heart of the Java type scheme. In the pizza paper, they already knew what was happening. They said this mismatch between languages is ironic. Java supports polymorphic arrays as best it can. As a result, pizza must offer less good support for them, because it turns out that this really is a big problem, and we'll describe this. So the reason you might, I guess probably most people know why this is a bad idea, but just to ram it home, given the previous declarations, you've got an array of numbers here is typed as an array of number objects, and so at compile time it looks completely legitimate to assign a double to an element of that array. But remember, the array carries runtime type information, so that doesn't work. And at runtime you get an array store exception. So you've converted, contrary to what we usually want to do, you've converted a runtime, what should be a compile time error into a runtime error, and this is a kind of basic reason why covariant typing is just a really bad idea for in situations where you want to put things into a container rather than getting things out. So that's when covariance really works. So what was the conclusion? Well, the way they handled this was in generic Java, which you remember was the second bite at this cherry of trying to get parametric polymorphism into Java. In the second, in generic Java, they came up with this scheme of erasure. And the idea of erasure is, well, it kind of basically, it's what it says. It means we're just going to erase all of the type information. The compiler will use it for checking the type safety of your code, but it'll throw it all away when it goes to the runtime. And in this way, they managed something that was really very significant. People complain a lot about erasure, but in fact, what they managed was to get very good adoption of the newly generified collections classes and a newly generified client code sitting on top of the old ungenerified libraries. And so this was an absolutely essential component of the migration path. Without it, we wouldn't have Java today.
Yes. So the type erasure, which was the decision that was made at some point in generic Java, is just this kind of thing that has been debated over for years now. Suppose you have an older class that is parameterized by the type T. T is just a parameter type, right? It could be really any type. And in this older, you have a field of type T, a constructor, and just a setter. Now, we all know that the class file in Java currently, and it was already the case in generic Java, only holds the object type for the type T. So the difference between the arrays of objects is that a generic type forget about the type of that is sent to it as a parameter at runtime. If I create an order of string or an order of integer, in fact, I will have the same class at runtime, roughly the same class with the same content, due to the fact that this type has been erased. So it means that if I want this code to work, right? If I want to prevent all the set of 10 to be legal, to be called on an order of string, which is the first example on this slide, it means that the compiler has to know the type, has to remember the type, and has to check for the error. So this is really checked at compile time. But now if you take an order that without its generic type and called set of 10 on it, beside the fact that it's an order of string, it will still work, and you will get a class exception when you try to get that object out of the order of string. So in the memory, this is not checked. There is no real check that you are really putting a pointer to a string or to an integer at runtime in this class.
Well, the slogan in Pizza was that they gave a cast iron guarantee. This is a kind of deliberate, laboured pun, that all of these, any cast that you're seeing like this here, would be bound to work, not ever throw an exception at runtime, provided you'd not ignored the unchecked warnings.
Yes, absolutely. So it also, when I do a get on the order, I do not need to cast this get to a string, which is some kind of magic. And this is also handled by the compiler, in fact, because the real get method you have in the class file just returns an object. So the cast has to be made on the call side where the method is called. If we check the bytecode generated by the compiler using ASM, for instance, from Remy4X, you can see what's happening really. You see, you have this older class, the order of T, and you can see that there is this synthetic bridge method that is generated by the compiler inside the class file. And this set method has been added just to handle what is kind of lost when it turns out that you need inheritance polymorphism and a real polymorphism using generics, right? Here we have a class that is string order that extends order of string. And if you want to create a set string method on this string order class, well, you have some kind of clash because you have two methods that turns out to have the same signature that should override the other one, and it doesn't, because in fact the method you have in order of string takes an object as a parameter, so it cannot be overridden by a method set that takes a string as a parameter. Thus, this kind of, how could you call that, a hack? I don't know. It's not a hack? Okay. Synthetic bridge method.
That's what they call it. That's not a hack at all.
And this is why you have this is synthetic property on the class class object from the reflection API. It's always confusing for many people. What does synthetic mean? Well, it's a kind of method that you can't really call, but it's still there. And this is the style. And you can see that in this synthetic bridge method, you have a check cast, which is basically a cast. All right. So it declares that set object. It gets an object at runtime, but this object is checked to see if it's really a string or not. That's if you call that without a string. Well, you can't call that without a string without getting an error.
It's kind of obvious why. I think it's kind of obvious why you would want this, because what Erasure actually consists of is replacing types with their bound. That's the technical description. And in this case, the bound for string. Sometimes it can be another type, but in this case, the bound for string is object. So at runtime, there is no set of string. Well, actually, there is a set of string method, but in general, the type has been removed, and so at runtime, it couldn't be found without the bridge method.
Absolutely. And so we have the same kind of thing with the get method as inheritance. If you want to have a get method, is a string holder that should really override the get method from the holder of string. Then you also need this you also stumble in this kind of problem, because this get method in the holder of t really returns an object all the time in the class file. So in the end, you also need some kind of synthetic bridge method in that.
Right.
So how is it working on arrays? Well, suppose you have an array of generics. Suppose that it would be legal in Java. We all know that it's not, but suppose it would be. It means that you can have an array of order of strings, right? That would be allowed if you had that in Java. But it turns out that an array of order of string, remember that this is what you said, and an array knows the types of element it's dealing with. So if you have both two arrays, an array that is an array of order of string and another array that is an array of order of integer, it turns out that those two arrays are the same because the types are erased from at runtime. So in fact, you end up having two arrays, not of string and not of integer, but two arrays of order of objects.
And you've lost your type safety.
You lost your type safety. And then since you have covariance with the types with the array type, it means that those two arrays can be assigned one in another, and there is no way you can type check that you can put an order of string in an array of order of integer. And of course, you want some kind of exception. Here, it's an array store exception.
You don't. You want to be not allowed to do it. I mean, the idea that it's nice to have an array store exception.
It would be nice to have it, but here you can't, because there is no information to throw this exception.
It would be even nicer not to be allowed to do it at compile time.
Absolutely. So it means that array of type type parameters are not allowed. Array of order of string are not allowed in Java, and that's the reason behind that.
So this is
array of generics can be created in Java.
Yeah. So this is actually really irritating. I mean, it's not so much that you're desperate all the time to be creating arrays of generics, but what is irritating is that when you learn about generics in Java, you have to think about these corner cases, all the things. It's not immediately obvious as to why it is you can't do that. I mean, we've explained it, but it's like, this was meant to be a really easy, intuitively obvious scheme, and now it looks to me like there's all these things that I can't do, and I have to learn what they are. I can't use instance of. I can't create arrays of generics. It's like, it's the cost of backward compatibility.
Absolutely.
Yeah. And it's the cost, in particular, it's the cost of having this covariant system of array typing. That was really the original sin. Okay. So in generic Java, they thought about what should be the right thing to do. Clearly, the right thing to do wasn't covariance. I mean, that was to make data structures uniformly covariant. Any data structure that you want to be able to put things into, if you make it always covariant, you're going to get the problems that we're talking about with arrays. So that's not on. It's not available. So list of integer can't be a subtype of list of number, because the code that you see there, the code that we're saying cannot work, is exactly the same code that we didn't want to have work with arrays. So what are you going to do instead? If we're not going to make list covariant, and we definitely don't want what's in the code box there, which is to lose the ability that they were so keen to have right from the start of having a generic sort method, taking that as an example, but generic methods in particular. What can we do about it? Well, I mean, we clearly don't want to have all these different methods.
That would be nice.
Yeah. So what can you do? Well, the answer is what you can do is you can have variant parameters. So instead of having covariant data structures, you can have types that have different variants on their different arguments, depending on whether those arguments are going to represent values you're going to put in or values that you're going to take out. So if you're going to take values out of a container, then you want to have a covariant type parameter, and if you want to put it in, then you want to have a contravariant one. That's the opposite. It's where I said that for a covariant type, it's easy to understand that integer being a subtype of number would mean that array of integer would be a subtype of array of number. Contravariant is the other way around. It means it'll be a supertype. So that the query extends number, which was the notation that was adopted actually in Java for parameter type variance. What that says is that the numbers list there is going to contain some unknown subtype of the type of number. And now we can define the sort method at the bottom there as being on a list of some subtype of number, in fact any subtype of number, and everything will work very nicely. As long as it's, in this case, it's okay for the type to be covariant because of course sort only reads values. It doesn't ever write any values in. So we've got lots, and you'll be really familiar with this, I guess. I mean, we're talking to an audience that now has been seeing generics and the collections utility class for the last 10 years. So you know that this query extends and query super are really, really common things to see in the signatures of methods that use generics. In Scala, they made a slightly different decision, and one that was in many ways a lot better, because they could have because they could write a new collections library, and in particular because they could define immutable collections, which are really in themselves a big step towards functional programming. They could have declaration site variance instead of use site variance. What does that mean? Well, what it means is that in the case of this slide here, we call it use site variance because it's the point at which you're going to make a call on you're going to make use of the list collection there, that at that point you have to define what's going to be the variance of the type parameter that you're supplying. So in this case we say, well, we want this to work on a list of number and on a list of any subtype of number. But if you had what's called declaration site variance instead, then you could define in this case, we've just used a slightly different data structure, a pair instead of a list. And the plus sign there in the declaration of pair says pair is going to be parameterized on some type T, and that type is always going to be covariant. And that means you can only ever take things out of a pair. But the upside of that is you don't have to say what variance you want to use. It's an immutable data structure. You can only take things out of it. And so the second line says that in this case, in Scala now, we're defining toString as taking a pair of any val. Any val is the top data type in Scala, like object is in Java. And if we were writing this in Java, we'd have to say query extends. But we don't have to do that. We don't have to do that in Scala if the declaration site variance, in this case the plus t, says I always want that. I always want this data structure to be covariant, and then you can make use of that in a much easier way. So declaration site variance moves the work from the client code. You don't any longer have to say for each individual type parameter whether you want it to be covariant or contravariant, because the data structure's already defined it for you. Now, the reason they couldn't do that in Java, they could do it in Scala because they could define these immutable collections, but in Java they were stuck with the JDK, with the Java Collections Framework, which came in Java 2. And they weren't about, in only a couple of years later, to produce a whole new collections framework. That was one was enough for them. And that's why we got use site variance rather than declaration site variance in Java. And up until now, I believe, and I'm pretty sure, there's still a JEP outstanding where there's a kind of speculation that we might get declaration site variance in Java, which would be kind of nice.
But does it mean that the sort method we just declared a few slides ago would be a nightmare to implement? Because the sort method will have to take out the elements from the collection, then sort them and then put them back.
Absolutely,
so
absolutely.
There will have to be a write operation somewhere. It's not going to work.
They very frequently internally they do mutation. But from the point of view, I mean, that's their problem, isn't it? I mean, library writers, who cares about them? We're client coders, aren't we?
All right. Maybe there are API writers in the audience.
All right.
Maybe we should respect those people.
To all library writers in the audience, I apologize. We really do care about you.
Okay, you stand there once again, please.
Okay, so that's a kind of very, very brief outline of the problems that they had with generics, or rather the evolution of generics, going from Pizza through generic Java to Scala and to Java, and some idea of why we got stuck with the problems that we've got in Java. This, of all the features, I would say, of all the three features we're looking at, what happened to generics shows the most problems in terms of backwards compatibility. Now we're going to go on to talk about higher order functions. So functions as first-class citizens are really they're the essence of functional programming more than anything else. They were the things that first came in. So we've got a very simple example here, just to show, why would we bother about higher order functions? Well, you want to be able to do things like this. You want to be able to have a max function which is going to work on a list and take some comparator. The top line is like a meta syntax, and the comparator takes two values of type S and returns a Boolean. And so the idea is that this max function will be able conveniently to find you the maximum of a list of S according to some comparison. And we look on this as a higher order function because the comparator here, the thing that takes two S's and returns a Boolean, that's a function itself. So so max is a function which works on functions. And it turns out this is really convenient. Functional programmers managed to write very elegant and concise code using higher order functions. And so there was, so they clearly wanted, that was a high priority to get that into Java, and that's what they tried to do in Pizza. They faced a big problem because you would really want a type system that actually encompassed the possibility of higher order functions. And actually the Java type system not only didn't allow for higher order functions, it didn't allow for functions at all. So object-oriented programs, object-oriented languages don't generally include functions. So their solution in Pizza was to create, for each function, they created an abstract class and with its own apply method. And so each function was kind of encased essentially in an object, so that it would fit in with the object-oriented way of doing things. And that actually has been the implementation all the way through. That idea is just the same one went through generic Java and to Pizza and to Scala. One question that they faced was the issue of whether or not to capture variables from the environment. Capturing final local variables is not a problem because they are because essentially that's a value. If it's final, the value can't change. But remember that what happens with a higher order function with a closure is that it can continue to live after its context has been removed. So capturing a variable means you've got a reference to a value, to a variable out there which can be changed by anybody, including for example, if this closure can be passed around, it can be changed by another thread. So that created a big issue. They didn't think about this in Pizza. They basically sat on the fence about capturing non-final local variables. The paper says, well, maybe you want to be cautious about this.
Maybe.
When it came to thinking about importing closures into Java, there was an extremely heated debate in around about 2006, around about just after Java 5, where the next big thing was clearly going to be bringing closures in. And there was a huge argument about it, and in particular, the issue was: are we going to have some really quite elaborate scheme which will actually allow the capture of non-local variables and will allow non-local return statements and various other things as well, and or something much simpler. And in the end, that debate kind of went away. But what was eventually implemented was something that really was very like the original Pizza scheme, the one that everyone knows really well, which actually uses not a single abstract method on an abstract class, but a single abstract method on an interface. And everyone knows about this because we know about functional interfaces since 2014, I think, something like that. Nice thing about this is it's a really neat way of preserving the type system of Java. You don't have to do anything very different. Lambdas in Java, we're not going to call them closures for reasons of the next paragraph, but lambdas actually fit pretty well into the type system of Java, because essentially they're just interface implementations. There's one or two things which aren't quite right about them. So, for example, the idea of identity, they're not really objects because the idea of identity doesn't work properly for them. But otherwise, they fit. It's really a pretty smooth fit. There was a definite decision made, though. They didn't sit on the fence about the capture of non-final local variables. They said everybody's writing code that assumes that your local variable is thread safe, that it belongs only to the thread that's executing the method that has declared it, and if you broke that by allowing those references to local non-final local variables to go out into the world and to be executed on other threads, that would just be a catastrophe for thread safety in Java, and they put their foot down. That was quite a controversial decision, especially to JavaScript programmers who think it's lovely to be able to pass these things around. But they don't care so much about concurrency as we do. Closures in Scala were really they followed the Pizza outline really pretty closely. They're really a fundamental part of the type system. They can capture vars, and we were talking about earlier on about how this works with concurrency with Amy Forax, and I said to him, how does that work with concurrency? And he had a straightforward answer. He said it doesn't. So it's really pretty dangerous. So the one thing that I wanted the one feature of closures in Scala, or let's say of higher order functions, that we thought worth bringing out here, and a parallel between Scala and Java, and showing different ways in which you can do things, was to focus on a feature that functional programmers really like about higher order functions, and that's partial application. So partial application, which you may know as currying is a way of achieving it, is where you have a function a function of two parameters. In this case, we're imagining that we've got a function that we're calling by, and part in this case the Scala method partial application is taking this function, and it's kind of splitting it up. It's returning a function which just takes a single argument, the second one, and it's going to compute the result of calculating with both of them. So it's like embodying the word, the string that By was expecting. It's embodying it in a function which will only need the second one after that. So now you've got the function f here in Scala ease just takes a string. And it just looks for it's going to find the index of where that string occurs in a word that has already been fixed for f. So, and you can get that by calling on the bottom line. You can see you get that by calling this partial application method, supplying the function index of and the word that it's going to embody. Scala's got a really nice way of doing this. You don't have to do all this in Scala because Scala really has currying. So provided you defined by on these two arguments separately, so you just put them in different argument lists. So we said that we want by to work on a word, and we want it to work on the string it's going to find within the word. Then f in this case can simply be defined. Partial application just works like magic here. You can just say I want to apply by to hello, and you get back a partial function which will just take the string that's to be searched within the word hello.
Absolutely.
So you can do it in Scala in Java as well.
You can do it in Java also. Of course, the syntax itself is really a Java syntax, so it's not as, we could say, clean as the Scala syntax.
Don't hesitate. It's not so nice.
It's not so nice, especially because, well, there is not this function type really. The type of function is in fact a functional interface. But we really at the heart of the partial application. Partial application is about taking, for instance, a by function, and by fixing one of the parameters of this by function, making it a simple function that is going to take only one argument. So here is the example. It's exact same example as the previous one, with the index of, search for a string in another string, and you have this by function that is going to take two strings, look for the second one in the first one, and then you just partially apply it to a fixed string of characters, exactly as you did, Maurice, on the Scala example, and this is going to give you a function that is going to search for strings in a fixed string of character that is passed as a parameter to the partial application. By the way, if you use this method reference stuff, you have default partial application. You're using the method reference syntax.
Well,
so
it's important to say it's a bound method reference. So it's a thing at the bottom. The bound. I was always really confused, even after I'd written a book about it. I was really confused about bound method references and unbound method references. But bound method references, basically, they're bound to the receiver. Like this thing at the bottom here, it's taking the receiver for this is already known. It's the string hello. So if you've got an object reference that the method reference is defined on, you've already got one of the arguments that the method is going to need already built in there. That's why this really is a nice parallel for partial application.
Absolutely. And that's it for the first fundamental operation of the functional programming we wanted to talk about. There is a second one which is called pattern matching, and this is what we're going to talk now and end this talk with this idea.
This was the third big feature.
Yeah, absolutely. And the nice thing is that we are going to have pattern matching at some point in the future in Java.
Some point.
And since it's much easier to foresee the future once it already happened, we are not going to give any date on that. But things are going very well, and we know that we are going to have pattern matching in Java. So here is how pattern matching in Pizza is working. It's basically a switch on types. Right, so you can define a class vehicle, and you can define two subtypes of this class. It's some kind of sealed type, that is, this vehicle is extended by the car type and the bus type. Basically, the car class is created on a single parameter, color, and the bus has no parameter because it's apparently only one bus. Fine. And if we want to create this capacity method that takes a vehicle as a parameter, and we have different kind of capacity attached to a vehicle depending on its color, for instance. So if it's a car, and you can see that here I'm stating that a car is in fact a car built on the color, and the pattern matching is able to deconstruct this car object. That is to extract this color property from the object and compare it to red. And if it's a red car, well, you can stuff 20 people in it. I guess they'll...
Makes sense to me.
Yeah, absolutely. Makes perfect sense. And if it's not red, then you can only stuff 4 people in it. So usually red cars are Ferraris, but Ferraris are really small.
This is a big Ferrari.
Yeah,
buses always take 12 people in our experience.
Bus always take 12 people.
Right.
There is no checking of the fact that the switch has or has not, must or must not have a default statement in it. So if you have other subtypes of vehicle and no default, then you're probably in trouble as far as the correctness of your code is concerned.
We're short of time, but I'd just like to say...
I'm confident.
You're confident. Well, let me...
I know you're not, but I'm not.
Let me remove your confidence by taking some time to say...
You want me to go on the previous slide then?
Yeah. By saying, well, like, why? How do object-oriented programmers feel about this? Like, how does this fit with subtype polymorphism? We never had this kind of thing in standard object-oriented languages. So, if you compare this with the idea of inheritance, you see that that this is going to be much worse. This is going to be a great deal worse for if what you want to do is add a new type. So if we have a new kind of vehicle, we're going to have to find all of the methods, like at the bottom here. We're going to have to find all of those, and we're going to have to add in another case for it. Yeah. So that's kind of quite bad. So, like, you know, and the kind of standard justification for inheritance and subtype polymorphism is that all you need to do when you add a new type is just to add that new type. That's all. But what if instead you want to add a new method to the supertype, like another method like capacity? So what you'll have to do with subtype polymorphism is you're going to have to add it to the supertype, and then you'll have to go around and find all of the subtypes that require it and add it in there. Whereas here, with this way of doing things, then to add a new method is just really all you have to do is just add a new method. So which of the two you would choose would depend partly on how you would expect your requirements to change in the future. Okay.
Program for the future. All right. So in Scala, you have sealed traits here. So you can also seal types, kind of types, in Scala. So we have sealed trait here, and a car that is also built on a color that extends the vehicle type we have, and a bus that is a singleton. Case object means that it's a singleton that also extends the vehicle. And we also have switch expression on types, which are mostly called match expression, because this is really a pattern matching with deconstruction. And the same as pizza, there is no checking on whether the switch is exhaustive as far as the hierarchy of vehicles is concerned or not. So the syntax is a little different. It looks like the lambda expressions we have with the fat arrow and stuff. But basically the syntax is roughly the same as the one we have in pizza. What we are going to have in Java is, of course, much better than that.
Flying cars.
Flying cars. The red car can now fly, which is nice, but it's not shown here on this example because we decided to remove it for the sake of simplicity, of course. So we have this new feature that is going in Java, which is the sealed type. Sealed interface with the declaration of a record class that implements vehicle and a static class bus that also implement vehicle. It means that the only extensions, as far as the type system is concerned, of the vehicle interface are contained in this sealed interface. Now, there's another syntax that allows you to create other types outside of this interface. And at the interface level, you will have to state that only the following types are going to be allowed with the permits keyword. And here we are using both a class, everybody knows what a class is in Java, and also a record. And a record is a special kind of final class built on the declaration of the elements of the class, of the car class. So it's called a record. And the compiler will do some wonderful things for you. We're not going into the detail for that. And once you have that, now you know that the hierarchy of the vehicle interface is complete, right? We know that we only have two types that extends vehicle, the car and the bus types, and that's it. So we can make exhaustive switch that are checked both at compile time and runtime. So it's much safer than what we have in Scala and Pizza. And we have another little cherry on the cake, which is that we can create case with the special value of the color property of the car type. We can have a case car, and if the car is red, then we are going to return 20 with this syntax with the meager row, which is of course much nicer than the fat arrow, no doubt about that. And the case stuff that takes a color that can be made a var, by the way, also so we don't need to repeat the type of color, and that we return 4. And this syntax does not exist neither in Scala or in Pizza, as far as we know. And the same, the bus is going to return 12 elements.
So it's fine. All going to be wonderful when it happens.
Well, we should have records for the record precisely. We should have record as a preview feature in Java 14. It's not yet in the early access, but it should be done quite soon. And the record Java 14 is next March, so it's really almost tomorrow.
This is a little further off.
Absolutely.
So, conclusion. Language design is really complicated.
Really? I didn't know that.
The design space is absolutely enormous.
I thought it was so simple.
And if you have to take account of backwards compatibility, it's really, really complicated.
Can't Monkey can design languages? Wasn't it our first slides?
Yeah. So what we've seen is that Scala has often been able to do things better, but it's done it at a cost of not only throwing away backward compatibility with Java, but actually that led to an attitude in Scala of not really caring as much about backward compatibility as Java has done generally. Java really puts backward compatibility onto a pedestal, and that influences the language design adversely in many ways. Certainly makes it much more complicated, but it has ensured that Java has kept the loyalty of millions and millions of programmers around the world. Brian Getz says, we don't want to be the first to include a feature because every feature we add will never be removed. How many languages can say that?
I don't know.
Okay.
I think that's all.
Yeah.
Thank you for attention.
Yeah.
We have a slide for that. Unfortunately, we don't have time for questions, so that's really very nice.